Right. Good morning, grade 12s. Welcome to another day in the life of online learning. Hopefully, you guys all coped with that. I did look at the ones that did upload their work, and thank you for doing that. It certainly helps me to see how you guys are going. You shouldn't have battled too much, I don't think. A lot of it was just number crunching. Okay, but we're going to use that concept today to be able to build up another concept and be able to hopefully tie those two in. Okay, morning, Lutfia. So we're going to have a look at a concept today. Now, what we've been working with yesterday is average gradient. Okay, the gradient between 2 points on a curve and how that can actually lead us to be able to find the gradient at a point. Right. But in order to be able to definitively work out the gradient at a point, we need to investigate a concept or an idea called limits, or the limit of a function. Right. And one of the ways that we can understand this, and hopefully this section leading on from what we've just completed with sequences and series, hopefully will make a little bit more sense as well. But first of all, let's examine a little robot. Okay, so let's consider the scenario where a robot is programmed to sense an obstacle in front of it and to calculate the distance from the obstacle. Right, so there's a little robot. It sensed the wall in front of it and it calculates the distance between it. Yes. Not a problem, Fazani. Welcome. Glad you could join us. Okay, so the robot is then further programmed to halve the distance between itself and the obstacle and then move to that point. All right, so the robot is now 8 meters away from the obstacle. And it keeps doing this over and over and over again. All right, now if we think about this theoretically, if this continues indefinitely, okay, so the robot is going to halve its distance, halve its distance, halve its distance, and move to the new point indefinitely, carries on forever. Theoretically, there will always be some type of gap between itself and the wall. That gap might be infinitely small, but theoretically, this robot should never ever reach the wall. Okay, because from here we will go to 2, then 1, then half, then quarter of a meter, 1/8 of a meter, 1/16 of a meter, etc., 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 etc. So we should never ever get to a distance that is 0. We'll get really, really, really close to 0, but we won't ever, ever get to 0. Okay, and that is the idea behind the limit concept. So practicality, it would probably, because the distance between itself and the wall was so infinitely small, it probably would bump into it at some stage. Okay. However, if the precision was there for the engineering, then it actually should never. So theoretically, in theory, when you're designing that thing, it'll never ever happen. Okay. And in that scenario, the wall would then be considered the robot's limit. Okay, so the limit, if we can think about it in that concept, then it's something that the robot would get really, really, really close to, but never ever reach. Now, it might come as no surprise to you that we've actually dealt with this in other places in maths before. Okay, think about asymptotes, right? If I've got the hyperbola there, my green lines are asymptotes. And the definition of an asymptote is a line that the graph gets closer and closer and closer to, but will never ever reach. And it was this concept of an asymptote of a hyperbola, the 1 over x, the bigger x gets, the smaller the 1 over x gets, but it'll never ever be zero. Okay, and it was that concept that we've just recently looked at and been able to work out the sum to infinity. Now we know that the sum to infinity will never ever exist because we'll constantly be adding something small on. But that what we're adding on is so small, it doesn't really affect the actual value significantly. So those are two places that we've actually already spoken about limiting values. Okay. And you'll remember that when we dealt with the sum to infinity, we actually had a look at one of the asymptotes. So let's now go on and have a look at limit values. Now, what am I talking about particularly when we're dealing with limit values? Okay, so let's consider our gradient demonstration that we did yesterday. Okay. Now, guys, I do understand that this is a rather abstract concept, and I've tried to make it as concrete as possible through these demonstrations. But I do need you to stop me and interrupt and ask questions if there's something that is not sitting well in your mind. Okay. Right. So the demonstration that we had a look at yesterday has f at x equal to x squared. Okay. And I must say thank you to Van for suggesting the idea that we've got a third point, because I hopefully that demonstration yesterday was able to show us that we were approaching a similar gradient at the point P. Okay, so yesterday we took a point Q and we brought it closer to P. We took a point R on the other side and we brought it closer to P from that direction. And as we brought those 2 points closer and closer and closer to P, we found that the gradient of the line segment joining P to Q and P to R was honing in, coming closer and closer to the same value, and that value was 2. Okay. We also acknowledged the fact that we won't actually be able to work out the gradient if P actually arrives at Q. I mean, Q arrives at P, because our X value then, or our change in horizontal, would then be a 0. And that we wouldn't be able to actually determine or calculate because we can't divide by 0. And what we're actually moving on to is we're moving on to a tool that will help us to work out the gradient at a point. It will help us to calculate instantaneous speed or velocity or anything else that has a rate of change, and work it out exactly at a particular time point or at a particular value on a curve. Okay. So when we took those yesterday and had a look at them, okay, we realized that we can use our average gradient if we get really close enough to give ourselves an estimate of the actual gradient at the point. And hopefully that exercise that you guys did yesterday enforced or reinforced that idea that we're getting closer and closer and closer together with the 2 points, and you would have seen that the gradient values were approaching a particular number. Okay, and that's the concept that we're going to work with today and build on. So that's just a summary of what I've just said. As the points Q and R get closer to P, their gradients got closer and closer to what we expect the gradient at P to be. Right, so we can say then that the limit of the average gradients is 2. Remember the robot demonstration? As it got closer and closer and closer to the wall, we said that the wall was the robot's limit. It was something that it was going to get closer and closer and closer to, but never reach, like an asymptote. Okay, so if we keep on moving Q closer and closer to P without going beyond P, and R closer and closer to P, again without going beyond P, then the limit of those average gradients, we can say that the value that those average gradients are approaching, that they're getting closer to, is the actual value at 2. And from there, we can estimate that the actual gradient of the curve at the point P is 2. And we're going to talk more about that tomorrow when we have a look more at the actual lines joining P and Q. Today, we're just really interested in the gradients of those lines. Okay. Guys, are there any questions so far? Anything that you're unsure of? Anything that you would like me to go over again before we move on? Okay. Right. So it's said that the limit of the average gradient, so in other words, the value that the average gradient gets closer and closer and closer to, is the actual gradient at the point. Okay. So that's quite an important fact. Let's have a look a little bit more at average gradients. Okay. So average gradient, or gradient in general, gradient of a line, we've come to know by using that formula. M is equal to delta y over delta x, and that delta was simply just a mathematical symbol to represent the change in y over change in x. Okay. From that, or if we expand that, that's actually what we're looking at. We're looking at y2 minus y1 over x2 minus x1. Those are the changes in the y values of 2 points over the changes in the x values of 2 points. If we now consider that y is actually an f at x, we've kind of grown away from using y's and started using f at x's and g at x's. Okay, since grade 10 when you were introduced to function notation. So if we then replace that, sorry, I'm getting ahead of myself here. So that is the actual gradient if the graph is linear, but the average gradient if the graph is a curve. So if the graph is a straight line graph, that gives me my actual gradient because my gradient is actually constant. It never changes. Doesn't matter where I go on that line, doesn't matter which 2 points I select along that line, the calculation of the gradient between those 2 points will always be the same. Okay. However, we spoke about this yesterday. If we've got a curve, okay, then if we've got 2 points on the curve, and we use that formula, then we're actually working out the average gradient. All right. And hopefully this is not a new concept to you. We did deal with average gradient when we went into the parabola in a lot more detail last year. Right. So that's where we need to realize that we're actually working with average gradient and not the actual gradient. Okay. This is where we start talking about our f at x. All right. Again, this should be quite familiar. It's very similar to the demonstration that we did yesterday. We've got the line PQ, okay? And at the moment, that line PQ is what we call a secant, okay? A secant is a line that passes through a curve in 2 places, but actually passes through it. So it's going beyond P and it's going beyond Q, the 2 points on the curve. Now, P has the coordinates x and f at x. There's no difference between saying x and y, okay? I'm just using f at x for demonstration purposes because the formula that we're going to work with, the final formula that we're going to come across tomorrow, is going to be including the f at x. In fact, by the end of the session today, you'll have actually found, you would have seen that formula that we're going to look at. Okay, so P has the coordinates x and f at x, right? So x is the x value at P, and f at x is the y value at P. If I now move P towards Q, so Q now is further along the x-axis from P. Okay, if I'm generalizing this, I don't know how far it is. Okay, yesterday we could work it out because we knew that Q was 3 units to the right of P. But if I'm wanting to generalize this, which is the whole point about creating a formula, we've got to be able to not work with a specific distance. So I'm going to call this distance between the x values of P and Q, I'm going to call that distance h. Okay, so that distance between the x values of P and Q is h. That means that the x value at Q must be what? Give you a moment to think about that. If the x value at P is x, and I've moved h units to get in line with Q, then the x coordinates of Q must be x plus h. Okay, so my coordinates, my x coordinate at Q is x plus h. That lines up with Q over there. And if I then want to determine my y value at Q, okay, I've got to read off there. That then determines my y value at Q. And if my x value at Q is x plus h, then my y value at Q must be f at x plus h. All right. Now I've got the coordinates of 2 points. Okay, I can now actually establish a formula in terms of those things based on for my average gradient. Now remember, average gradient, just be called average because we're dealing with a curve, it still uses our gradient formula. And remember, our gradient formula is change in y over change in x. So we take the y coordinates of Q and subtract the y coordinates of P, and then the same thing with the x coordinates of the 2 points. So if we substitute what we know are the coordinates of these 2 points into this little formula, we should get the change in the y, which is f at x plus h, minus f at x, over x plus h, which is the x coordinate of Q, minus x, which is the x coordinate of P. That then we can actually simplify just to read as f at x plus h minus f at x all over h. And now I have a general formula, or I have a formula to work out the average gradient of any function between any 2 points. In fact, I can work it out exactly as long as I know the x value of the points, okay, of the 1 point. Right, so that's our average gradient. And I know we've taken something that looks as simple as change a delta y over delta x, and we made it look really complex, okay? But there's actually a reason for that. There's a reason why we've made it look that difficult. And what we want to do, excuse me, is we want to tie these two together, the two concepts that we've had a look at in this presentation this morning. We want to tie them together. Remember, as I'm bringing Q closer to P along the curve, okay, the average gradient of the line PQ is heading towards being the exact gradient. Okay, so if I can work out what this thing is heading towards, okay, then I can actually establish what the actual gradient is. And what we've got to understand and realize is that as Q moves closer and closer and closer and closer to P, what is happening to H? Well, as Q is moving closer, the X value of Q is moving closer to the X value of P, which means my H is becoming closer and closer to being 0. And if we have a look here, that's going to present a problem. Okay, but we have a way around it. And this is where we start looking now at gradient at a point. Right, so remember, it is said that the limit of the average gradient is the gradient at the point. So in other words, to calculate the gradient at P, we need to move Q closer and closer and closer to P. We've been speaking about that the whole of yesterday and the whole of the lesson today. But what does that mean? As I said just now, this means that H, the distance between the two X values, is getting smaller and smaller and smaller and getting closer to being 0. So, as P heads towards Q, okay, and in this section, that arrow over there actually means tends to. So as P tends to Q, we can say that H tends to 0. And obviously, if P tends to Q and H tends to 0, our average gradient is going to tend towards being the gradient at the point. Okay. So our gradient at a point, we're then going to determine or calculate the limit as H tends to 0. So in other words, we're going to ask the question, what is, if you look at this formula here, you should recognize this as being my average gradient formula in the previous slide. So as my average gradient, or what this is asking is, what is the limit? In other words, what value is my average gradient approaching as H approaches 0? Okay. Now, there's been quite a lot that you guys have had to try and absorb in this lesson, and some really, really, really abstract concepts that you have to actually try and work through. Okay. We've had about 25 minutes of quite intensive concentration and being able to work through this. Okay. And guys, I really hope that you are actually following with and going through this and taking notes and whatever, and not just relying on the fact that this video is going to be posted and this PowerPoint is posted, and you can just listen to it when your brain's fresher or whenever you feel like it. So I really hope that you are following along and are sticking with as we go through this. Okay. So again, I just want to reiterate what we've done here. Limit, remember, the limit of the average gradient is the gradient at the point, but the limit also asks, what is this thing, what is this expression approaching, getting closer and closer and closer to as H approaches 0? Now, obviously, we can't put 0 in there because that's going to present a problem. Okay, so what this finally will give us is a gradient at a point because it knows, or we're able to calculate what this thing is approaching. Okay, so I haven't given you any work today. I haven't given a worksheet to do or anything. I want you to be able to absorb this, but I do want you to work out and see if you can calculate the gradient of that curve at that point. Okay. I know I haven't done an example with you. I really do want you to be able to just work through this. I will go through this example with all of us tomorrow in the lesson tomorrow. But I want you guys to try and work through it and get to a solution yourselves. The answer here, by the way, is 4. So the gradient of the curve, f at x equals x squared minus 1 at the point 2, 3, is 4. So if you're able to get the answer of 4, going through the process or going through using that formula there, gradient at a point, okay, then that's fantastic. Right. Then you sort of well equipped and ready to go through tomorrow. But that is it for today. I will go through this example step by step tomorrow. Um, but I would really, really, really like you guys to be able to work through that yourself, and to be able to, if you're able to get there, it's going to be wonderful. And those of you who've done AP Maths with me last year, don't cheat. Okay. But guys, I know there's an example, a worked example in the textbook. Try and avoid using the textbook, try and avoid going through that. I really want you to just spend 10, 15 minutes trying to get through this on your own. But having said that, please don't panic if you can't. Okay, I know I haven't gone through the worked example. I'm wanting you to try and work through it, and then we will go through that example together tomorrow, and then you will have some examples or some questions to be able to try tomorrow as well. All right. Are there any questions, Matrix, grade 12s? Right. Guys, as you work through that, I do expect you to battle, and I'm not trying to make you battle, but I do want you to work through it. What I do want to say to you is use substitution, use factorizing, and use simplifying. So those are 3 clues that should be able to help you get through that. And you use those clues in that order, by the way. Substitution, factorizing, and simplifying. Cheers, Al. Thank you. Bye, Zappa. Bye, Rach. Bye-bye, Siamo. Cheers, Roman. Have a good day. You too. Thank you.